All right, so 10.5 is continuing on with probability, which is what we did in 10.4. It's just taking it one step further. We're talking about independent and dependent events. So what we've done for the most part going up until this section is we're talking about probabilities of one event. And what we're going to do moving forward is talk about probabilities of more than one event happening. In other words, doing two things, like this and then this. And, you know, we've done a lot with playing cards and what you draw, like is it, you know, what's the probability of us getting a king, or what's the probability of us getting a king and a diamond, but only taking one card. What this section is going to be more about is what's the probability that our first card is this, and then what's the probability of the second card being this. So it just kind of takes it to the next level. So we have to make a couple of definitions here of independent events and dependent events. The independent events is what you might think it is. It's basically saying when each event has no effect on the other. Sorry about my writing here. It's not very good, but you can obviously write a lot smaller than me. So when each event has no effect on the other, which means dependent events is exactly the opposite. It's when one event depends on the other or affects the other. Okay, and then conditional probability, this is a little bit different, but I'm going to write out some notation. You guys have seen a lot like P parentheses A, like the probability of A. But what you'll see is this is going to be the probability, and you'll see a line in between, but it'll be probability of B, and then there will be this straight line down the middle. And what this means is this means the probability of B if A has already occurred. Okay, so it's conditional. Probability of B conditional to A already occurring. Okay, so and I'll write that out. The probability that B will occur given A has already occurred. Okay, so again, it'd be like saying we need an even number. You know, we want an even number. Here's, you know, we're going to put numbers in a hat 1 through 50, and we want to know what the probability is that we'll get an even number given that it will be even. So like given that it's going to be an even number, what's the probability that it'll be 4? So what it does is, given that it's an even number, it would take down the number of choices that we have, so the probability ends up being better because it's conditional probability. We'll see a couple of examples. Okay, so let's talk about independent events. It says if A and B are independent events, then the probability that both A and B occur is P of A and B. Well, this is really simple. All you're doing is multiplying. It's the probability of A times the probability of B. So in this case, we've seen a lot of the probability of A and B, but now we're talking about independent events, so two separate events. Okay, it's not about like the same event of both happening. It can be, but in this case, we're talking about this is going to happen and then this is going to happen. Both are going to happen as separate events. You multiply the two together. Okay, it says more generally the probability that n independent events occur is the product of the n possibilities of the individual events. So let's just look at an example and see how this works. It says every morning one student in a class of 24 students is randomly chosen to take attendance. What is the probability that the same student will be chosen 3 days in a row? So all three of those are different events, day 1, day 2, and day 3. Okay, those are going to be the student being chosen on the first, second, and third day respectively. The three events are independent, so therefore the probability looks like this. It will be P of A times P of B times P of C. Okay? And what that ends up being is 1 over 24. That's the probability that the one student gets chosen. And then the same student is 1 over 24 again. And then the same student is 1 over 24 again. You multiply those three fractions together, you get a pretty small number, but that's what you would expect in a situation like this. So it's 0.0000723. And in your calculator, you would have gotten, times 10 to the negative fifth power. I just kind of already figured out what that would be. But again, all of them are separate. 1/24 of a chance, 1/24 of a chance, 1/24 of a chance. You multiply all of those separately by each other, and that's what our probability is. Okay, let's move on. Second example. It says, this one we're going to use a complement, and we're going to talk about that briefly. It says a manufacturer has found that 2 out of every 500 coffee pots produced are defective. What is the probability that at least one coffee pot is defective in the first 300 coffee pots made? So this one's a tough one, because what you guys need to be able to figure out is anytime you start seeing things like this, at least one is defective. Well, that would be really hard if we were just, 2 out of every 500 are defective. Well, if we want to find out if at least one is defective, then why not just figure out when a coffee pot is not defective? It makes it a lot easier, because all we have to do is, once we know when it's not defective, all we have to do is figure out 1 minus that, and that will give us the answer. Okay, because when it says at least one, if we go the other direction, then we would need to figure out if one is what's the probability of 1 being defective? What's the probability of 2 being defective? What's the probability of 3 being defective? 4, 5, 6, all the way up until 300. That's impossible. So when you see that you'd have a ton of opportunities or a ton of chances for it to be like that, then think of what it would be for 0 and then just subtract that from 1. So what we're going to do is we're going to find what's the probability of the coffee pot not being defective. Well, we look at this. 498 out of 500. That is the probability of it not being defective. Okay, so what we do is we start with that, and that gives us a decimal of 0.996. So what we're going to do now is, that doesn't mean that our probability is going to be 1 minus 0.996. We're not quite done yet, so let's keep going down, because now we're talking about 300 coffee pots made. So what we're looking at here is, this is the probability that it will not be defective in 1 pot of coffee. So if we wanted to do this 300 times, we would do this 0.996 to the 300th power. And that's what we're going to have here. So it's going to be 1 minus this to the 300th power, because we have to do it 300 times. So literally, remember, this is an independent events. Coffee pot number 1, what's the probability of it being defective? Or sorry, what's the probability of it not being defective? 0.996. That's the first one. Second chance, what's the probability of pot number 2 being not defective? 0.996. And you do that 300 times. That's where this exponent comes from. Okay, so we do that to the 300th power, and you get 0.300. So therefore, 1 minus that is going to give us the probability that at least one of them will be defective. So we actually have a 0.700 chance that it will be defective. Okay, that's out of 300, which again makes sense. Okay, when you do that many pots of coffee, eventually one of them is going to be defective. Okay, hopefully that makes sense. What I want you guys to do is do these checkpoints below. These are the ones that you'll do on your own, and then just hit play when you're ready so you can see what the solutions are. All right, so in the first one, you should have gotten 1/27. Why? Well, you have 3 lanes to choose from out of 9. So that gives you a 3/9 chance or a 1/3 chance each time. So 3/9 times 3/9 times 3/9, or 1/3 times 1/3 times 1/3 equals 1/27. So that's the probability that you would be in lanes 1, 2, or 3 each time. Okay? So that's real simple. It's just multiplication each time. They're all independent of each other. The second one is, again, the same way as we did the second example. You figure out how many are not defective, so it's 444 out of 450. And because we're going to do it 100 times, we would multiply that to the 100, we would raise that to the 100th power and then subtract it from 1 to find out whether a battery is defective. So these are not defective. So 1 minus not defective gives us probability of defective, and you get 0.739. Okay, so moving on from there, let's talk about dependent events. So these are where they are actually dependent on each other. And here, this is how it works. So it says if A and B are dependent events, then the probability that both A and B occur is the probability of A times the probability of B knowing that A already occurred. So this is where the conditional probability comes in. And again, this isn't really much different. It's just kind of understanding how the problem works and what's going to happen. It does change it a little bit, but not much. So you'll see, and it's pretty logical on how it will change. So let's look at an example. That's the second page of your notes. Okay, so in this case, we have a chart with a bunch of information given. It says find the probability that a listed person has blue eyes. So let's start with that. A listed person has blue eyes. So what we do is we add up the two blue eyes, which is 44. So the total number of people with blue eyes is 44 over the total number of people. This is just regular probability, what we did before, and that's over 200. Okay, and this ends up getting us 44 over 200 is 11 over 50 reduced. Okay, so that's our fraction there. That's the probability we've been doing. But let's talk about this. It says, what's the probability of blue eyes given that the person's going to be a male? So that changes things. Because now we don't even need to worry about the female column anymore. We only worry about the male column. Okay? So we just look at 35 is definitely the number of males that have blue eyes. So that's what we write here. We do 35. And then on the bottom, it's just going to be the number of males. So it's 35 over 100, and that reduces down to 7 over 20. So really the only thing with conditional probability, it's just pretty much telling you what you can get rid of, because we're not, we're only trying to find out what the probability of getting blue eyes are, knowing that it has to be a male. So all it does is eliminate some of our possibilities, so the probability actually goes up. All right, let's look at a different example. Okay, it says you randomly select 2 marbles from a bag containing 15 yellow, 10 red, and 12 blue. What is the probability that the first marble is yellow and the second marble is not yellow if A, you replace the first marble before selecting the second? Let's start there. Okay, because we're replacing it back, both of our events here are independent. That's very important. They're both independent because we're replacing it. So the probability is just simply going to be the probability of A times the probability of B. So we just figure out what the probability of each one is. We have 15 yellow, which is 15 yellow over a total of 37. And then we have 22 that are non-yellow, so it's just 22 over 37. You multiply those two together, and you get 330 over 1,369, and that as a decimal equals 0.241. Again, all we're doing is multiplying our two events together. Well, let's talk about when we do not replace it. So this is a little bit different because now it's P probability of A and it's probability of B, but given that A has occurred. So that changes things. So now, because these are dependent of each other, it does change it a little bit. So let's look at that. So the first one will still be the same. It'll be 15 over 37 because there's 15 yellow out of 37 total. The second one, there still is going to be 22 non-yellows, but now we don't have 37 anymore, we have 36. So now we multiply these two together and we get 330 still on top, but the number on the bottom is less. It's 1,332, so our probability actually goes up a little bit. 0.248. Not much, but it still goes up. Okay? All right, so what we're going to do is we're running out of time here, so this is going to go into a second video, but we don't have a ton of time that we need to spend on this. Probably another 3 or 4 minutes, but I want to make sure that we don't get cut off. So go ahead and we're done with this video, so make sure you watch part 2.